Well, welcome back. So today what I want to do is continue and probably wrap up sparse QR factorization. I want to move on to LU, which is, although I might not get that far today, LU factorization is more frequently used than QR factorization, but QR provides the basis for the theory for LU. LU was the first sparse matrix algorithm because it's the most important of the three factorization methods, but it comes third in the book just because of the theoretical basis. Okay, so I left off, hopefully now you see how this works. Okay, the idea here, let me just recap, is that we've got this matrix R, and we know the non-zero pattern of it ahead of time because it's the Cholesky factor of A transpose A. And we have a column of R, and we have to take every one of these non-zeros and use that to apply a householder vector to the entire vector, right? Because this one has to be applied to all the entries below it, of course. But we don't have to, if this entry is not a child, then it doesn't take part in the symbolic pattern, because if it's not a child, its parent or grandparent or ancestor will be a child of K, and all the non-zeros that appear in this column that's not a child will then appear up the chain in the tree. So let's ignore this one in terms of the pattern. Then what we need to do is take the children and apply the householder operations. And what I showed you was that these have to be disjoint. So if this is non-zero, this has to be 0. If it wasn't, then if this is also non-zero, then that entry would be non-zero and it wouldn't be a child. So we have a disjoint property here. And so let me draw this in a peculiar way. Let me put, say, all the non-zeros in the column of A first, but only those that satisfy this property here. Only those rows that are in the leftmost. So the leftmost column is K, and I showed that if it isn't, then that row will appear in the householder vectors of the children anyway. So if you have a row index in A here and you've got a non-zero out here, it will then appear in one of the children. So that's disjoint. And then I also showed so this is disjoint, this is disjoint, and that's just disjoint. So we just have to add these things together. It's a very simple process. Doing the set union, it would just be a matter of concatenating these values. And that's really useful because there's two reasons why we want to know the non-zero pattern of this column. Well, there's multiple reasons. Okay. One of them, we want to know the size of the householder vector that we're going to have to use to apply to this, because we're doing the symbolic analysis. We want to know how many non-zeros are going to be so I can lay out the work for the numerical factorization. So I want to find the count. But I also need to find this row permutation that as I go, I want to put a non-zero on that diagonal. Okay, so if this is 0, when I come to factorize it, if that diagonal is 0, and if I compute the householder has one extra non-zero in it, that then all the column counts are off. So that's not good. So what we want to do is take one of these entries here of the updated matrix A prime, or A bracket K. This is the matrix. This is the column after all the householders have been applied. We just want to pick one of these non-zeros and stick it there. So how do we know which one to pick? it doesn't have to be one of these entries. It can be actually any. So what is the non-zero pattern? Is just the concatenation of these three regions that I've drawn here. So how do we actually find a specific row index to put there? Well, the solution is to keep track of what rows we can easily keep track of in constant time these actual sets of those three rows. And here's the idea. Okay, it's because of the concatenation property. We're just going to be concatenating linked lists together to create this structure. So I don't have to actually traverse these lists to find their pattern. This is the neat thing about QR factorization. There's things you can do that are asymptotically very fast but don't require a huge amount of theory. Okay, so the idea is let's suppose you've got a column of A with no children in the tree. Okay, so no householders apply to it. If no householder entries apply to it, then all of the non-zeros here are the leftmost in their particular. All those column indices are the leftmost non-zero in their particular row. Because if there was a non-zero out here, then, well, this row would have taken part in an earlier householder. And if it did, there'd be this row gets replaced with the non-zero pattern of the set union of these other rows. And A would have a child. The column K would have a child in R. I mean, there'd be a non-zero there. So, well, we can't have that. If it's got no children, it's a leaf, and this all has to be 0, right? Otherwise, it's going to have a child. So these, if I've drawn them, 3 of them, these are all the rows I, such that K is the leftmost non-zero. Okay. So that's easy to start. Now, what happens after we do this householder? Well, before we do the householder, I need to say, before we do the householder, well, this is the set from which we have to pick. We've got to pick one of these 3 and stick it there on the diagonal. But I have this list. I can easily form this list in order n time. Order n and z time, because I've swept through the matrix to do this. I have this list, and I just pick one of them. Pick the head of it. In fact, it doesn't matter which one you pick. So just pick the head of the list. So it's constant time selection. So I've got a linked list of 3 items. Pick the head. Okay. Well, now what about the other 2? The other 2 precisely describe the householder vector. So this gets put here. We put one of them there, permuted up to the top. The others that remain in that list is the non-zero pattern of that householder vector. So now think of this inductively. I have this from my child. If I have this from my child, so that's the base case. The base case is that if you have no children, your householder non-zero pattern is just that linked list of the leftmost minus 1 that you chose arbitrarily to stick up there, permuted. Okay, so now by induction, let's suppose we're supposed to have a list of the non-zeros here, here, and here. Okay, we have this. That's we've found out on input. Let's assume by induction that you've got the pattern of these 3 stored in a linked list, so you can easily concatenate those lists together. Well, if I have if I have the lists of all my children and the list of myself, I can just concatenate those 3 lists together and then pick any one from that list, and put it here. And that gives me the non-zero pattern of that householder vector. So in time equal to the number of children I have, because every child, I've got constant amount of work to take this list and concatenate them together, because I have a head and tail pointer to that list. So linking multiple linked lists together just takes time proportional to the number of lists, not the length of the list, because you don't have to traverse them. If you know the head and the tail, you just glue them together. So the total work of building the list across the whole graph will be order n, because each The sum total of the number of children in the graph is n. So if I know the list for my children and my list, then I know me. And then by induction, I've solved the problem. I've got the base case here, and I've got the inductive step here. If I have no children, I know what my pattern is. And if I do have children, well, if the children know who they are, then I know who I am. And we're done. Proof by induction. So that also provides an illustration more, because this theorem requires further statements which I've made. But so that's the concatenation of these sets together. They're all disjoint. So that's handy. And I can then actually compute as I go this list. So let me show you now how the code does it. Okay, so this is the symbolic QR factorization. And so what's happening here is, I've already gone through part of it before, but let me just recap. We've got the row permutation vector, okay, and it's a little larger than you might expect. It's actually because of rank deficiency, we have to have a special case for that. So I make it bigger just in case of that condition. That's an issue I'll talk about later. But we've got a row permutation. We compute the leftmost, and we get some workspace here. And then the workspace is for several things. It's going to keep track of the head and tail of each linked list, and the next. So the sets of n linked lists are going to be held in 3 arrays with a head and a tail and a next. Every node has a head. Every linked list has a head. Every linked list has a tail, and every node has a next. The head and tail pointers are of only a size n because we have only one linked list per column of the matrix. So this has n columns, but there's m rows. So every row gets its own next pointer. So next is of size m, but head and tail are size n. And then I've got this other variable nq, which is n, not en, but n as in the number. Okay, it's the size of each of these lists. So nq of k is the number of entries in the kth linked list. So it's the size of these 3 sets here in particular. It's the size of this set here. So that's easy to keep track of. When I create the list, I can count how many I put in the list. And then when I glue those lists together, well, the size is just the sum. And then when I pick one off, I just have to decrement. I don't have to ever traverse the list to count if I can just keep track of the count. And so this NQ then is going to give us, at every step, the column counts for the V vectors, for the householder vectors. So the first thing to do, again, we compute the leftmost non-zero in every column. So that's what this phase of the code does. And then the next thing that happens is the linked lists have to be initialized. So we go through and we initialize the row permutation to be undefined. Grab the leftmost column index of row I, and if the row could be completely non-zero, in which case k will be -1, if so, skip it. And then just insert row I into the kth list. That's what these 3 steps do. And if the Q starts out as empty, if this NQ of K is 0, which is being incremented because I'm putting one thing into the list. But if NQ of K is 0, then I have to assign the tail, and then just otherwise, in any case, it just sticks onto the head. And I do this in reverse order just to try to preserve the natural order, so that when I go to choose, I'll tend to pick a low row index rather than a high one. It's just more aesthetic. It's not necessary. It's not required. This is just more of aesthetic. Otherwise, you just kind of flip your matrix upside down, and it's weird when you're trying to understand what's going on. Because you pick the head of the list, it's the last row, not the first one. It's kind of odd. So then the body of the loop then goes for every k. All we got to do is grab the head of the list and say, you're this chosen one. You're the one that goes in the diagonal, if you exist. The linked list might actually be empty. It's a special case. But that's one more count in L and Z is actually the matrix V. So there's two matrices here under consideration. There's the R matrix and the V matrix. But this symbolic object S is used for LU, Cholesky, and QR factorization. And since this V is lower triangular, if I take the vectors V and pack them together, it's a lower triangular matrix. And there is no lower triangular matrix in QR factorization, so it's natural to use L instead of V in the symbolic structure. So this counts the number of non-zeros in the V matrix. So there's the assignment. It's like, okay, row I, you're the kth row on the diagonal. And that row I gets removed from the queue. And where does that happen? Head should advance to the yeah, that's done here. Head's going to advance by 1. So now I've got this. Now I've got this single linked list, and what I've assumed here at this point is that I've already got the linked list, and so let me revise the induction step a little bit. What's happening here, what I do is I do the work of the child. I don't want to iterate across the children and say, oh, let me go to each of my children and concatenate those lists together, because I don't have, the elimination tree points from child to parent. The parent doesn't know who the children are. You could compute that, right? And I do in some cases, but I don't need to, if I don't have to, I would rather not. And so what happens is then once the child is finished computing its structure, it appends itself onto the linked list of the parent. So that's what's happening here. We're done. At this point, we're done with column K. Okay, and we've got the number of non-zeros in that V vector right there. We're done. In fact, I don't even store the vector of the column counts. I just have to store I just want to know the total for the QR factorization. It doesn't actually need each individual column count. I just want to know the total so I can allocate some static space for it. Then I determine the parent, and if I have a parent, then my linked list has to go on to the linked list of the parent, and that's the constant time work here. There's no loops. I'm not iterating across the linked lists. That work then just says, okay, take this linked list of row indices and append it onto the tail of the linked list of the parent. Except, of course, if the linked list of the parent is empty, then there's no tail at all. Then the tail of the, let's see. So let me draw what's happening here. I've got the parent I'm calling Pa, and I've got K, a linked list. So there's these two linked lists here. So this is head of K, and this is tail of K, and the parent linked list looks like this. There's the tail of the parent, and this is the head of the parent. And these links in the middle are the next. So if that's a row index, then next to that row index gives this next row. Okay, so now I want to concatenate these together, and I'm going to put it at the head of. So this is row I here by definition. And row I is getting destroyed. Row I is getting chosen. It's getting removed from this link. So that's what's happening here. I want to point the next, so let's look at this carefully, next to the tail of K to the head of the parent. So that takes this. So this is the next of the tail of K, points to the parent. So that's this step right here. Then I want to take the head of the parent and point it to the next of I. That's this step here. And now the linked lists are glued together. And all I got to do then is to know the total, I just have to increment the number of entries in the parent, and then has been incremented by 2. So it used to be 3, but it's been decremented once right here. And then the only other twist is that if the parent list was initially empty, okay, then this right here must now point to the tail of K, because this used to be null. And if this list was null, pointing the head to here is fine, okay. And now that points to a valid row index. Or null if the list is empty. Okay, you have to worry about the empty case. And then this doesn't change if there's one or more items in this list, then tail of the parent doesn't change at all. We've just appended this list of the child onto the list of the parent to the front. But if there's nothing in this list, this is still null, and I don't want it now to be null. I need to point it here. So that's what this first statement does right here.
So why are you putting K in front of the parent instead of the other way around?
Oh, I don't know. I could have done it the other way. I could have put, the question was, why am I putting the list of the child to the front of the parent instead of at the end? I don't know. That's just the way I chose to do it.
Good enough.
It is. I mean, it felt more natural to me. I don't know. To stick it on the list, stick it at the head of the queue. That I think putting at the end of the queue, I might have would have had a few more lines of code here or conditionals that say, well, what if the because this list here might be empty. And if the child list is empty, there's no work to do. Okay, so that's taken care of already. I know that the child list now has something in it. The list of K has at least one object in it. So I'm taking a list of size that's 1 or more and appending it onto the front of a list that might be of size 0. And that, to me, felt a little easier to do it that way than the other way around. Because if I've got a list of no size, so these are null, head and tail of the parent are both null, and I've got a linked list here that I want to append to the end of an empty list. What does that mean? I'd have to worry about, see, if I have a list here, so this is now the new head of K. Actually, it's next of I now. Okay, because I've deleted I. So this is next of I. So I have a list of 1 or more items here. I'm going to append to the empty list. Well, I have to have the special case to say, well, okay, if that's the case, then the head and tail have to be just pointed straight here at the end. Otherwise, the tail, I mean, then, I think it's just more lines of code is all it is. So otherwise, if you've got something, stick it on the end, you've got to take the next here and point it there and update the tail, and the head doesn't change. So the tail becomes the tail of the new list. I guess that happens in any case. The tail becomes the tail of the new list. next to, yeah, it probably would actually, as I think about it. Here the head doesn't change, here the head does change, but that's also a conditional here. It might be the same. So, yeah, playing with linked lists is kind of fun, and I don't know, I just picked a method. No, there's no technical reason at all. It would end up giving you a different row permutation, but who cares? Because any row permutation is fine. And that's it. And then at the very end, I want to go through and finish off the row permutation. So m, in fact, could be larger than n. Okay, in which case, I've got to stick something there. I mean, I want to wrap up the row permutation. Okay, so every row has to have a place. Now, there's one more twist to this, which is kind of awkward. And that's this little piece that I glossed over. Okay, this little piece I glossed over is adding a fictitious row. What is that? It's possible that the matrix can be structurally ranked efficient. Okay, but that breaks all my theories. I've always said, the diagonal. Let's for simplicity make all the theories work that the diagonal is zero free. Suddenly, well, what if you do a QR factorization of a matrix that's all zero, for instance? Oops. What do? Well, you've got to stick an entry there of zero value, but it's got to be structurally present for the theories to work. So how do we pick? I mean, this is awkward then. What if we've got the QR factorization of a matrix that looks like this? Okay, I do the QR factorization. I say, okay, you're it. You're on the diagonal, and the v vector is empty. Okay. I come here and I realize, oops, my child has nothing, and I have nothing. There's no row to put here. This list here of candidate rows will be empty. There's nobody to put there. So who do you put there? Well, if you do put this row there, then you're ripping away a row which is going to appear in a different linked list. This guy is a different place. You got to go find the thing and take it out of where it was and put it. It's very ugly to do. So I wave my hands at this. I say, no, forget this. Let's just pretend we're doing a QR factorization of a bigger matrix. So if I have this happening, I pretend by appending on an identity of all zeros. So I'm doing a QR factorization of a larger matrix on the fly. I create a larger matrix. And it's going to give me the same QR factorization. The R is going to be the same. The R doesn't change. Q gets sort of stretched out a little bit, but that's okay. And what happens here, then, if I run out, if you will, if I come to a column that says, oops, I fail here structurally, there's no entry to put there, well, then I just pick one from here. And this matrix actually doesn't have to be identity. It can just be created on the fly. And so I say, oh, fine, I've got rows in one base notation. I've got rows 1, 2, 3. They're all accounted for. I can't just pick row 2 and put it there because that row 2 is going to be accounted for in the QR factorization of column 3. So I can't rip that out for my parent. That'll change all the theories. So let me just glue on a new row 4 that's all 0. It's numerically all 0, but with a structural entry right there, and then let me swap that in instead. And so what happens is, if you will, this matrix is dynamically growing by one row, and it's this entry that I put on the diagonal, and then these two, rows 2 and 3, continue on as before. They're not affected. And so that's what this does. This plus plus says, give me a new fictitious row. and let me call it M2, which starts out, M2 is the number of rows in the existing matrix. And so if I want a new one, I just increment. So that gives me a row to put there. And then this will be 0, right? The queue will be empty. If this is negative, then the number of entries in the queue is negative. So all I do is I pick a fictitious row and go and finish. So there's no extra work to do. So that's a little bit awkward. It's really an ad hoc solution to the problem. Okay, this is not a very elegant solution to this problem. It really is ad hoc. I don't like it. Okay, but to do it right would require far more work and far more code than I was willing to invest. And it would handling structurally ranked efficient matrices in a proper way the code would be much more complex, and it would hide the key features of this QR factorization, and the essential nature of the QR would be hidden behind all this nasty code. So it's a one-line fix to the problem. A little inelegant, but it works, and to creating that fictitious row. It's just that now when I use the QR factorization, I have to keep an eye out for those fictitious rows in the Q matrix to say, oh, okay, you're a row 4. You're past the end of the actual matrix, so you're all 0. Nothing happens to the row. It stays 0. There's no householder applied to it, right? It just stays 0. But then when Q is applied to this matrix, if I do Q transpose times AX minus B, okay, Q transpose now has a fictitious row in it, and it's going to grow B correspondingly. B has to be appended by zeros as well. So the Q transpose times A will give you this R matrix that's been increased in row dimension by a little bit. That doesn't affect X, you see, because X is governed by the number of columns of R, and that's not changing. So X is not affected. But then what has to happen with B, if I stick extra rows of zeros on here, I have to conceptually append zeros onto the rows of B. That doesn't change the norm of this vector, right? Because it's the square root of the sum of the squares, and it's just 0 and 0. So I can still solve a least squares problem this way, sort of. I have a ranked efficient least squares problem actually, and R, the matrix R, in fact, would look just like this. Well, actually, it doesn't look like this. This gets swapped up. It's going to look something like that. There's my R matrix. Because this row will get swapped up, and then these two rows, 2 and 3, will be, a householder will be applied to zero those out. And so that's my R matrix. I've got an entire row of all zeros in my R matrix. Now try a triangular solve with that, right? When we're trying to find the least squares solution, we're going to do a triangular solve. We'll get a divide by 0. So you can't, if you have a ranked efficient least squares problem, you can't solve it in the normal way. You'd have to do something called a complete orthogonal decomposition. You'd have to apply householders not just to the left but to the right. There is a solution around this, but the machinery is very high powered. You have to do a lot of extra work to handle this case. But with this small fix, I still get QR equals A. Well, I just get this instead. Okay. So R, I just had a few zeros here, and Q gets bigger. I still get a QR factorization of a matrix, and that matrix includes A as a submatrix. So I still get what is a usable QR factorization. And I can determine that it's ranked efficient as well. So that's kind of handy. And with a single row. A single line of code by adding a row with one line of code. So that's what's happening there. And this is why at the top that this row permutation vector has to be of size n plus n, because you could have a completely zero matrix, in which case you've got to add n fictitious rows to the problem. That's the upper bound. So I just allocate the upper bound, and I don't have to worry about what happens after that. So that's the symbolic factorization. Now I know how many non-zeros there are going to be in the householder vectors. I know, and I could have, had I wanted to, I could actually keep track of how many are in each householder vector, because I did compute it. Okay. Where was it? Right here. There's the diagonal, and the Q is decremented by 1, and then I add the rest of it here. If I didn't have rank deficiency, I could just add the length of the Q and it'd be done. But I have to add 1 for potentially the fictitious guy, and then everybody else then as a separate case. That's why I added, increment it twice here. But the total number of times I increment this by 1 and this by the length of the Q, that is the length of the householder vector for that kth step. And I can keep track of it if I wanted to. I could store it and stick it in an array. I don't preserve it because I don't need it. But I have it here had I needed it. It's available. So it is computing the column counts with much simpler theory than, because it's just concatenation. It's much simpler theory than the column counts for Cholesky. But we've already got the row and column counts for R, and the pattern of R, and the children of R, and the finding this non-zero pattern, and that's just straight out of the Cholesky problem of A transpose A, not of A. So then the entire QR factorization then looks like the following, and this is just gluing together all the previous stuff we've seen so far, except for this piece right there. That's chapter 7. That's the only look ahead, if you will, because there's really no way of doing this early. To do a fill-reducing ordering, you have to understand what the factorization is going to do first before you can decide how do you permute this matrix to reduce the fill. You've got to know what it's doing first. So conceptually, this has to come last in the book. But of course, it's done first in the computation. So the very first thing is a fill-reducing ordering. And if that fails, we kick out. And then we have a choice here. If we're doing a QR factorization, so for the moment that's what we're doing, so forget the stuff down here. Then we have to take this matrix, permute its columns. So this is a column ordering on A. Because the row ordering doesn't matter. It's the column ordering that affects the fill-in. So the matrix is permuted. We find its elimination tree. And this flag is 1 that says, hey, I'm not finding the elimination tree of this matrix C. I'm finding the matrix of C transpose C. And then do the post ordering on the tree. Find the column counts of the factor R, which is it finds the row counts, actually, of R, which is the column counts of L, of the matrix C transpose C, so that flag is 1. And then we do this V count algorithm here, which I just showed up above, to do the counts of all the non-zeros in V, and to finish off this row permutation to assign entries to that diagonal. And then the non-zeros in R have been computed up here. So I just get the total count here, sum it up, and then I'm paranoid about integer overflow. So if integer overflow occurs, then I want to know it. And so that's what this check here is for. And then if I did have to permute the matrix, I free this C matrix. If I didn't permute this, if order is 0, that means you're going to use a natural ordering. If this integer selection parameter here. 0 means natural order. 1, 2, and 3 mean various different kinds of orderings. And if it's 0, then what's going to happen is I'm just going to pick A itself. So C and A will be identical. So I don't want to free C if order is 0. If order is 0, I've got the C is the input matrix, and I don't want to free that. So that's the total symbolic analysis. And that gives me that gives us the total counts of the vector of all the householder vectors, and now we know that the counts for R as well from the Cholesky factorization, symbolic Cholesky. So that's everything. Now we can look at the numerical factorization. And that is here. So again, that's kind of long. I wanted to scroll off the screen here. So the numerical factorization is fairly straightforward now that we know how big everything is. We just have to go one by one and say, okay, at what has to happen now? What has to happen is at the kth step, we're going to go column by column. And if we're at the kth step, I have to take each of these non-zeros in R and take the first one and apply it. Take this first one and apply it to this householder, to the rest of the matrix. And then take the second one and apply it. Whoops, I drew it wrong. And take all of these and apply each of their householder vectors to this kth column, including the upper triangular and the lower triangular part. So I take the kth column of A, apply all these householders to that. The top part then becomes a piece of R, and the bottom part then becomes the householder vector for the guys to the right. So then at the end of the work, then the householder vector here needs to be computed and stored. So that's all that happens. So this whole first page is just setup, right? There's just getting memory space, getting out stuff from the matrix and the symbolic analysis and the leftmost and so forth. So we just go through because let's see. We allocate our the V matrix, the R matrix. We've got the number of non-zeros in the householder vectors V and Z, which is here, and R and Z, which is the number of non-zeros in the upper triangular factor R, or it's U and Z in the symbolic analysis. And now at this point here, because I've got to do gather scatter anyway, I just use that. I simplify this code. I don't try to keep track of the patterns of V using the linked lists anymore. I mean, I could have done that, but I chose not to. So here's the kth step, and it goes all the way down. It keeps going all the way down to the bottom. I wonder if I could close some of these. Ooh, yeah, that's cool. Okay, so what happens then is I need to keep track. You see, what I don't know at this point is I don't actually have the column pointers for R. You see, so I'm having to do some symbolic work in this step anyway, on the fly. Because the R matrix has been transposed, if you will. It's the lower triangular matrix, L for the Cholesky that's been flipped. And the Cholesky, I have the column pointers for Cholesky, but that would be then row pointers for R. But I don't want R stored by row. As I compute it, I need it by column. And when I'm done, I want to produce a column-oriented matrix. Now, I can each step find, and I'm going to do this down below here. I'm going to have to find the non-zero pattern of the kth row, and I'm going to do that by traversing the elimination tree right here. Basically an eReach code. So I've got to find this. And I know the total count of number of non-zeros in R, but I've got to, at each step, find that kth column of R. So that's what's happening here. I don't know where my column pointers are, so I just keep track of we just keep track of the number of non-zeros in R, and then that's going to be incremented as we go. So we've got the start positions of these R and P vectors. We're just gluing these on to the end of this matrix. So R and P are growing from left to right. So that's convenient for a column-oriented matrix. At the kth step, I'm computing the kth column. So R is growing by column, V is growing column by column. And I know how big these data structures are because I've counted how many non-zeros are going to be in the result exactly, assuming numerical cancellation doesn't occur. And so I'm just going to find these non-zeros patterns and then glue them on. Okay, so the first thing that happens, of course, is the diagonal is there, and that's marked. This right here is a trick. I think I've shown it to you before. This is a flag vector W. It's integer. Okay, and I'm going to be using it to do the symbolic set unions and marking of nodes in the tree as I walk up the tree. And so it's going to be initialized to -1, and now what I can do is say that, well, at the kth step of the algorithm, if Wi is equal to k, here's an example right here. If Wi is equal to k, then the node has been marked. If Wi is not equal to k, then the node has not been marked. Well, at the very next step, k is going to increment, which then means the whole array, W of I, is all false for all I, because Wi will never be equal to k, because k just got incremented by 1. So it starts out at -1, and then when k is 0, I've got a whole vector of -1s, and there's no Wi that will be equal to 0 except the ones I make 0. And then when k increments to 1, nobody will be equal to 1 until I start setting values equal to 1. So I never have to reset this flag vector, this mark vector. So then to find the non-zero pattern, we've got to look at the we've got to grab this A matrix here. So I've got the kth column of A, and I've got some non-zeros in it. Each of those rows, though, in the kth column, I want to find the leftmost in each of these, okay? Because this is going to define the search up the tree. So let's see. I need to go back and look at the symbolic analysis for R. When we're, and I'm just about out of time. So if we've got this, in fact, I am out of time. So let me stop here. But in the tree of R, we're going to have to look at the leftmost of every row to walk up the tree. So it's slightly different than eReach, but with this change, we have this eReach code, and then that'll compute a path that gets stuck on the stack. Then that'll give us a collection of entries in the V vector. So this is computing the non-zero pattern of V and R together, and then the next step will be to do the numerical work. So I'll pick up here. I'll explain to you why this symbolic work is, how it's working, then next class on Monday. And so we'll hopefully then finish up QR factorization at that point. So, and I will see you then. Thank you.